So we will practice with some example about the gas logs. Let's look at this example. First of all, be careful with the conversion of the unit. Don't forget what we learned in chapter 1. The dimensional analysis to do the conversion of unit. So here, the given unit, always start the given unit times the factor. This factor, how you will write it down, you have to put the wanted unit in the top, and in the bottom, it will be the given unit. You cancel the given with the given, and you will end up here with the wanted unit. So this is the dimensional analysis. If we need to use more than one factor, you have to arrange it in a way to cancel all the given and you will end up with the wanted. Look to this example here. High-performance road bicycle tire is inflated to a total of pressure of 125 psi. What is the pressure in millimeter of mercury? So you will start with 125 psi times what? So look at here, guys. This gives you the unit of the pressure of the sea level, atmospheric pressure. So with the Pascal will be 101.3, 101,325 Pascal. Atmosphere, it will be 1 atmosphere, 760 millimeter mercury, 762, 14.7 psi, 29.92 inch mercury. So we will look for the relationship between the psi and the millimeter mercury. You will write it down over the top. It is the 760 millimeter mercury, and in the bottom it will be the 14.7 psi. So we can cancel psi with the psi, do the math right now. So we will have 125 divided, 125 times 760 divided by 14.7, it will be 6,000. So it will be 6,462.6 approximately millimeter mercury. Okay. So let's go to this example right now. cylinder occupied with movable piston has an applied pressure of 4 atmosphere and a volume of 6 liter. What is the volume of cylinder if the applied pressure is decreased to 1 atmosphere? Yes, when you have when you have two situations, initial and final, it's meaning change in the situation could be one of these equations, T1 V1, V2 V2, or V1 divided by T1, or V2 divided by T2, P1 divided by T1 equal P2 divided by T2, or look at those number V1 and 1 equal V2 divided by N2. Or the combined class laws, which is P1 V1 divided by equal P2 V2 divided by T2. Now, look to the change, the information that has changed here. So we have pressure, so P1, it is 4 atmosphere. V1 was 6 liter. Now we need the volume. So the P2 here will be 1 atmosphere. The V2 will be unknown. So we will use the P1 V1 equal P2 V2, and the V2 here will equal P1 V1 divided by P2. And that will give us what? The P1 is 4 times the V1, which is 6 divided by P2, which is 1, and that will give you 24 liter. This is the answer. Let's look for second example here. Okay. A sample of gas has a volume of 2.8 liter and unknown temperature. When the sample submerged water temperature equals 0 Celsius degree, the volume decreased to 2.57 liter. What is the initial temperature in Kelvin and Celsius degree? Assume a constant pressure to distinguish between the two temperature scales. Use T for the temperature in Celsius degree and capital T for temperature in Kelvin. Now guys, here always the temperature in this chapter calculation or question, always use it in a Kelvin, which is the Celsius degree plus 273.15 to get Kelvin. So look to the information that we have here. So we have volume V1 equal 2.8 liter, and T1 here was unknown. V2 here it is 2.57 liter, and T2 here it was 0 Celsius degree. This 0 plus 273.15 will give you 273.15 Kelvin. Now, which equation we will use? We will use this chapter. So here, V1 divided by T1 equals V2 divided by T2. We need to find the T1. So it will be V1 T2 divided by V2. And here the V1, the V1 was 2.8 liter. times T2 273.15 Kelvin divided by 2.57 liter. Yes, a liter, do the math. So we will have 2.8 times 273.15 divided by 2.57 give you 297. 297.6. So here will give you 297.6 Kelvin. Now this is in Kelvin. Now temperature in Celsius degree will be 297.6 minus 273.50. And that will give you the temperature in Celsius degree. So here minus 273.15, it will give you 24.4. So here it will give you 24.4 Celsius degree. So let's go to this example right now. A sample of gas has initial volume of 150 milliliter, air pressure 735 millimeter mercury, and a temperature of 34 Celsius degree. If the gas compressed to a volume of 108 milliliter and heated to a temperature 85, what is the final pressure in millimeter of mercury? So let's see what we have here. So we have, first of all, the V1 for 158 milliliter, and our pressure, so P1 will be 735 millimeter mercury, and at temperature, so it will be T1 also 34 Celsius degree. Now let's change, so the gas compressed to a volume, so V2 108 milliliter, and T2 is unknown, and the T2 here, it is 85 Celsius degree. First of all, this 273.15, you will get it in Kelvin. So this is the first step. So 34 plus 273.15, we will get 3 of 7.15. Now let's do the same things for 85 plus 273.15. So the plus 273.15, and it will be 358.50. Now, which equation we will use? So look at here, when we have these variable, no constant except the number of moles, so we will use the combined gas law. So P1, U1 divided by T1 equal P2 divided by T2. Here we need to find the P2, so it will be P1 V1 times the T2 divided by T1 T2. That will give us the P1 is 735 times the V1 158 times the T2, which is 358.15 divided by T1, which is 307.15 times the V2, which is 108. Be careful, guys, also with the unit. Cancel and end up with millimeter mercury for the pressure. So here let's do the math. So we will have 735 times 158 times 358.15 now divided by 307.15 divided by 108, and that will give us 1253.8 millimeter mercury. It is the P2. Okay, so let's practice with this new example here. So let's look at this example. A 4.8 liter sample of helium gas contains 0.22 mole of helium. How many additional mole of helium gas should you add to the sample to obtain a volume of 6.4 liters? Assume a constant temperature and pressure. So what do we have here? V1 4.8 liter and N1 number of moles, that is 0.22 mole. An additional mole to get the V2, it is 6.4 liter. The N2, it is N1. So we will use this formula. V1 divided by N1 equal V2 divided by N2. So here 2. So the V1, it is 4.8 liter divided by 0.22 mole will equal V2 6.4 liter divided by N2. Now N2 will equal 6.4 liter times the 0.22 mole divided by 4.8 liter. Cancel this liter with this liter. Do the math and we will get here 6.4 times 0.22 divided by 4.8 and we will get 27. So here we will get 27.68. How much do we need? No, guys, just let me check the math. I think, there's like 6.4 times 0.22 divided by 4.8. Oh, sorry, guys. So it will be 0.29 mole. So it's 0.29 mole. Okay, so let's keep going and practice with another example. calculate the volume occupied by 0.845 mole nitrogen gas at a pressure of 1.37 atmosphere and temperature of 315 Kelvin. Now, if you notice here, we don't have a change in this situation. We don't have initial and final situation. In this situation, we will use the gas laws PV equal nRT. So here, PV equal nRT. We give you the number of moles, 0.845. R is a constant, 0.08206. Temperature, you have to do it in Kelvin, it's already in Kelvin, so 315. And here, we give you 1.37 atmosphere. And they ask him for the volume. Volume is unknown. So here the volume will equal what? Now be careful guys. The pressure, when we have PV equal nRT in this equation, here is supposed to be atmosphere, volume in liter, N in mole, T in Kelvin always. And R will be liter times atmosphere divided by mole times Kelvin. Now here the volume will equal nRT divided by the pressure, and that will equal, so the N it is 0.845 mole times the R 0.08206 liter atmosphere divided by mole times Kelvin times the temperature 315 Kelvin, and all these divided by the pressure, which is 1.37 atmosphere. Now Kelvin will be cancelled with this Kelvin, mole cancel with this mole, atmosphere with this atmosphere, then we will do the math and our unit will be in liter. So here we will have 0.845 times 0.08206 times 315 divided by 1.37, that will give us 15.9 liter is the volume. Let's go to another example. Calculate. Okay, we already did this. Okay. Let's see this example right now. Okay. Calculate the number of mole of gas in a basketball inflated total pressure of 24.2 psi with a volume of 3.2 liter at 25 Celsius degree. So here, if you notice also, we don't have initial and final situations, so we will use the PV equal nRT. PV equal nRT. So don't forget, guys, the unit here is very important. Pressure is supposed to be in atmosphere always. Volume in liter, N in mole. R is a constant. Liter times atmosphere divided by mole times Kelvin. By the way, R, we have a different number according to the unit, but here we will use the 0.08206. Temperature always in Kelvin. Now, if you notice the pressure here, it is not in atmosphere. So the first step, we need to convert the psi to atmosphere. 24.2 psi times the conversion factor between atmosphere and psi. 1 atmosphere give you 14.7 psi. Okay, so this one with this one, do the math, and we will get here 24.2 divided by 14.7. And it will be 1.65. So here approximately 1.65 atmosphere. Now, temperature. Temperature here, it is in Celsius degrees, supposed to be in Kelvin. So it will be 25 Celsius degree plus 273.15, and it will be 298.15 Kelvin. Volume in liter, so we are fine. So here we will say T will equal nRT divided by the V, and it's already in the mole here, isn't it? Oh, sorry, they need to calculate the number of moles. So here, N, sorry, they need to calculate the number of moles. Okay, so N will equal the PV divided by RT. Okay, what is the pressure? It is 1.65 atmosphere times the volume, that is 3.2 liter, divided by R, which is 0.08206 liter atmosphere divided by mole times Kelvin times the temperature here, the T, it is 298.15 Kelvin. Okay, so Kelvin, liter with liter, atmosphere with atmosphere. Do the math and your answer will be in mole. So let's do the math here. So it will be 1.65 times the 3.2 divided by 0.08206 divided by 298.50. And that will give you 0.2. 0.215 more. That's the solution. Excuse me. Okay, so let's go and check this. Okay, we have these two questions. Let's move these also. So, number one, how much volume? How much volume does 0.556 mole of gas occupy when its pressure is 750 millimeter mercury and its temperature is 58 Celsius degree? Okay, let's start with number one. Two questions here. So number one will be also PV equal nRT. So nRT. And here we need to calculate the volume divided by nRT divided by the pressure. But be careful, guys. Careful with the unit. Here and number one, we are fine. But here, the pressure in millimeter, we need to convert it to atmosphere temperature, Kelvin. So first of all, here the pressure 715 millimeter mercury times conversion factor in atmosphere atmosphere in the top, 760 milliliter mercury in the bottom, and that will give you 715 divided by 760, give you 0.94. Give you here 0.94 atmosphere. For the temperature, 58 Celsius degree plus 273.15. And that one will give us 58 plus 273.15. So it will be 331. 331.15 Kelvin. Now I've substituted these values, the pressure and temperature. And that is 0.556 mole times R, which is a constant 0.846 liter atmosphere mole Kelvin. Okay, times the temperature, which is 331.15 Kelvin, divided by the pressure, which is 0.94 atmosphere. So Kelvin with Kelvin, mole with mole, atmosphere with atmosphere, to the math, and here the V will equal, quickly here, so we have 0.556 times 0.0826 times 331.15. Now the result divided by 0.9, we will get 60. So here will be approximately 60 liters. Question number 2. Find the pressure in millimeter of mercury of 0.133 gram sample of helium at 32 Celsius degree contained in 648 milliliter container. And so we will use the PV equal nRT here. We need don't forget, we need here the amount of the sample in mole, we need it. And here, and we need it in Kelvin, here in liter, and they are asking for the pressure. First of all, here we have a mass, we need to convert it to mole. So it will be 0.133 gram times 1 mole helium. We will use the molar mass, and 4 gram helium. Let's do the math here. 0.133 divided by 4 will give you 0.033. 0.033 mole. Next, we need to do the temperature, 32 Celsius degree plus 173.15. So here it will be 305.15. Yes. Kelvin. Now for the volume, 648 divided by 1,000, we will get it 0.648 liter. Now substituted in this equation, so we will have the pressure will be nRT divided by V. Here, the number of mole is 0.033 mole, and the 0.08206. We will have the liter atmosphere divided by mole times Kelvin. All of this times the temperature, Kelvin, 305.15 Kelvin. Divided by the volume, 0.648 liter. Now we will cancel Kelvin with Kelvin. mole with the mole, liter with the liter. Our answer will be in atmosphere. Let's do the math. 0.033 times 0.08206 times 305.15 divided by 0.648. We will get 1.2. Here we will get 1.275 atmosphere. Now they are asking in millimeter mercury, so we have to convert the atmosphere to millimeter mercury. So here, 1 atmosphere will be 760 millimeter mercury. That will give me, so here times 160, give me 969. 969 millimeter mercury. Let's go and practice with other. Okay, sample of gas. Sample of gas has a mass of 0.311 gram, its volume 0.225 liter, and temperature of 55 Celsius degree, pressure of 886 millimeter mercury. Determine the molar mass. Here they are asking for the molar mass. So here they are asking for the molar mass. From what we done previously, we have a relationship between mole, mass, and molar mass. The mole will equal the mass divided by molar mass. So we need to calculate the molar mass here. We need mass divided by mole. So the molar mass will equal mass divided by mole. Now I have the mass here in this equation, but I don't have the mole. So here, from this information, I will try to find the number of moles. So PV equal nRT. N will equal the PV divided by RT. Don't forget the unit, guys. So this is a volume we are finding. This one plus 273.15. It will give us 300.15, so it will be 8. Okay, so 328 from 15 Kelvin. And what about this one? So this one will be 886. We will divide it by 760. Divided 760. Convert it to atmosphere. So let's see, we will have 886 divided by 760 will be 1.7. 1.17 atmosphere. So here we will, here, so the pressure 1.17 atmosphere times the volume, it is 0.225 liter divided by R, which is 0.08206 liter, atmosphere divided by mole times Kelvin, or this divided by temperature, which is the 328.15 Kelvin. Cancel Kelvin with the Kelvin, atmosphere with the atmosphere, liter with liter, and my answer will be in a mole, so it will be what? We will have 1.17 times 0.225, the volume, divided by 0.08206 divided by 328 will give me 0.01. It will be 0.01 mole of oxygen. Now the molar mass equal to mass divided by mole. This is the mole and this is the mass. So here would be 0.311 gram divided by 0.01 mole. That will give you 31. So 0.311 divided by 0.01, 31.1. 31.1 gram per mole is the molar mass. Okay, guys, don't forget to be careful with the unit. It's very important to do the value for the unit and deal with these type of questions. Okay, so let's see what we have here. Okay. A mixture of helium, neon, and argon has a total pressure of 558 millimeter mercury if the partial pressure of helium 341 and the partial pressure of neon was 112. What is the partial pressure of argon? P total, it is the summation of the partial pressure of all the gases that we have in the mix. So here it will be the pressure of helium plus pressure of neon plus the pressure of argon. Total pressure was 558 millimeter mercury. Partial pressure of helium is 341 millimeter mercury plus partial pressure of neon 112 millimeter mercury plus partial pressure of argon is a known. You need to calculate. So here, the partial pressure of argon will be 558 minus 341 plus 112. That will give you, so here we will have 3, 5, 4. Here it will be 5, 0, 105. So it will be 105 millimeter mercury is the partial pressure of argon. Let's look to this example. How many liters of oxygen gas form when 294 grams of KClO3 completely react in this reaction, which is used in the initial part of our work? Okay, assume that the oxygen gas is collected at pressure 755 millimeter mercury and temperature 305. So they are asking how many liters of oxygen, volume here, of gas form if we have used this mass of KCl. Now, let's look for the information that we have for calculating the volume of oxygen gas. We know P equal nRT. So here, to calculate the volume, we need the PV divided by, for the volume will be nRT divided by the pressure. This is the pressure after you convert it to atmospheric. Use it here. This is the temperature. This is the constant number of moles of oxygen gas. We don't have it. Now, be careful. This mass is for KCl3. And what we are looking here, it is the number of moles of O2, of oxygen gas. What we learned previously in the stoichiometry, we can use the mole-to-mole ratio to find the mole of any chemical if we have the mole of the mass of the other chemical. So here, we will start with 294 gram KClO3. We will convert it to mole. Using 1 mole KCl3 divided by the molar mass of KCl3. KCl3 will be Cl 5.5 plus oxygen will be approximately 122.5. So 122.5 gram KCl3 and times the mole-to-mole ratio between oxygen and KCl3, which is 3 mole O2 divided by 2 mole KClO3. And we will cancel more KCl3 with this one, ground KCl3 with this one. Now let's do the math. 294 times 3 and divided by 122.5 divided by 2, we will get 3.6. We will get here 3.6 mole O2. Now I have the mole of O2. I can use this equation to calculate the volume. So this one, volume will equal nRT divided by the pressure. That will give me the number of mole 3.6 mole times 0.08206 liter atmosphere divided by Kelvin is mole times the temperature, which is 305 Kelvin divided by the pressure. Now the pressure, you have to divide it by 760 to get it in millimeter mercury, so it will be approximately 0.95 atmosphere. You can just take the math. Okay, so atmosphere with the atmosphere, mole with the mole, Kelvin with Kelvin, and our volume will be in liter. Let's do the math here. It will be 3.6 times 0.08206 times 305 divided by 0.95, and we will get 94.8 liter. 94.8 liter is the volume of oxygen gas. Be careful, guys, with these type of equation of stoichiometry involving the gas.